guys, what's up? So I am Munot and welcome to the School of Physics. So today we are going to do rotational dynamics. Rotational dynamics is a very simple chapter. A lot of people fear this chapter, but I'll make it seem easy. So let's start a quick revision of rotational dynamics. Okay, so you have to learn a few basic concepts, and since your exam is objective, a lot of those questions can be directly solved through formulas or basic concepts. All you need to do is understand it. Okay, so today we are going to do rotational right dynamics. We are going to do rotational dynamics. Alright, so rotational dynamics, the story of rotational dynamics begins with the moment of inertia. Now what is the moment of inertia? Moment of inertia, I is equal to mr square. So in suppose this is our origin, right? This is our origin, and here we have a mass m1, here we have another mass m2, here we have another mass m3, and here we have mn, right? So these are the four masses, and this is the r1 vector, this is the r2 vector, this is the r3 vector, this is the r3 vector, and this is the rn vector, right? So we have n particles like this. So the moment of inertia in this case will be very simply written as I, which is a scalar quantity, is m1 r1 square plus m2 r2 square till mn rn square, right? So it will be the summation of all the individual moment of inertias, I1 plus I2 till In. It is the total moment of inertia of this system of particles. Okay, now I'll tell you some very basic moment of inertias. Questions come directly on these formulas. So we have, so moment of inertia is always seen around an axis. Moment of inertia is always seen around an axis. So suppose we have a ring here, right? This is a ring. So the ring's mass is m and this radius is r. So the moment of inertia will be mr square. Now this is a very good and important concept, that suppose I extend this ring downwards, suppose I make a lot of replicas of this and I turn it into a hollow cylinder. What I do is I turn it into a hollow cylinder. So the moment of inertia of this when extended downwards will be equal to the moment of inertia of the ring, which is also equivalent to mr square. Now this is a concept. Suppose we have a disk of mass m and radius r, and this is a disk. Now the moment of inertia is mr square by 2. The moment of inertia is mr square by 2. Now if I extend it using the same concept and make it a filled cylinder, make it a solid cylinder, then the moment of inertia of the solid cylinder is also equivalent to mr square by 2. Now if I take a part of this disk, and I ask you what is the moment of inertia, so we take any part of this disk, its moment of inertia will also remain mr square by 2. So we take any part of it, its moment of inertia will also be mr square by 2. This is derived in your books. It is through uniformity. You have to keep this in mind. Now suppose we have this. We have a rod here, right? We have a rod, moment of inertia. So this moment of inertia was calculated by around an axis passing through the center. This moment of inertia was also calculated around an axis passing through the center. In case of rod, the moment of inertia of this rod of length L and mass m, right, passing through the center, and now there's this rod of mass m and length L, but we are seeing the moment of inertia passing through the edge. So the moment of inertia in this case, the moment of inertia in the edge case will be ml square by 3, and the moment of inertia of this rod when the axis is passing through center will be ml square by 12. The moment of inertia will be ml square by 12. Similarly, if we have a triangular plate, a rectangular plate of edge A and B, so the moment of inertia would be ma square plus b square by 12. The moment of inertia will be ma square plus b square by 12 if it is passing through the center, right? Now I'll ask you a question, very simple question based on the same concept. Suppose I turn this rectangular plate into a cuboid. I extend it into a cuboid. I extend it. So what will be its moment of inertia? Okay, so its moment of inertia is also going to be ma square plus b square by 12. So this is a solid cuboid, and its moment of inertia will also be the same. Cuboid, its moment of inertia will also be the same. So I guess you got this concept. So we have two more theorems, very simple theorems on moment of inertia. I'll use this space. So one is parallel axis theorem and another is perpendicular axis theorem. Okay, very simple to understand, parallel axis and perpendicular axis. So suppose I have an object, right, and suppose I take a plate. I'll take a plate. So the moment of inertia around the axis iz, the moment of inertia around any axis iz, so I have this plate, suppose the moment of inertia around any axis iz will be equivalent to sum of the moment of inertias of the two axes, any two axes that are perpendicular to it, So what I mean to say is iz is equal to ix plus iy. What theorem is this? This theorem is called as perpendicular axis theorem. Now the next theorem that I am going to tell you is parallel axis theorem. So in parallel axis theorem, what will happen in parallel axis theorem? Suppose you have the same plate, right? And this is the center of mass of the plate. So I center of mass. Now we take an axis which is parallel to the axis that we drew passing through the center of mass. This can be any axis in any angle. Now we'll take an axis which is parallel to this axis. So this is called I parallel. Now the distance of this axis from the center of mass, suppose we call it d, and the mass of this object is m. So what perpendicular axis theorem says is I parallel. That means I of the axis parallel to the center of mass is equal to I center of mass, that is moment of inertia when the axis is center of mass, plus md square, plus mass into distance between the center of mass axis and the parallel axis ka whole square, right? So I parallel is equal to I center of mass plus md square. So this was all you needed to know about moment of inertia. Okay, there's one more thing I can tell you about moment of inertia. It's called radius of gyration. What is it called? It's called radius of gyration. What happens in radius of gyration? What happens is a very simple thing. So I by m, so as the name suggests, radius of gyration, as the name suggests, it is denoted by k. It should be in the units of radius. So we know the formula for I is mr square. So if we divide it by mass and do an under root, what will be the units? It will be the unit of radius. So you'll be getting direct questions, since it is an objective exam. You'll be getting direct questions where you have to just remember the fact that I upon m under root is called the radius of gyration. Okay, so we move on to the next part of this chapter. I hope this moment of inertia thing is clear. It is very easy, very simple concepts, very simple questions will come on this. So rotation isn't as hard of a chapter as you think that it is. It is not that hard of a chapter. So the next thing that we are going to talk about is angular momentum and torque. So angular momentum in a rotational motion is similar to momentum in a translational motion. So and torque in a rotation motion is similar to the force in the translational motion. So we have two things we have to remember. Angular momentum is denoted by L vector is equal to r cross momentum. Okay, and this is also I omega. We have to remember this directly. This is also called I omega. And torque vector is equal to r vector cross f vector. Torque about any point is the distance vector of that point cross of the force that is applied on that point, that is r cross f. We can remember it as I alpha. Omega is the angular velocity and alpha is the angular acceleration of any rotating body, Okay, so then we also have this, what is the kinetic energy? Kinetic energy in terms of rotation. Kinetic energy in terms of rotation is equal to half I omega square. You can check the units. The units are of energy and it will come out in joules. So kinetic energy rotation is equal to half I omega square. Now okay, so the next thing that I'll teach you is going to be angular momentum is equal to r cross p, torque is equal to r cross f, kinetic energy rotation is equal to half I omega square. Okay, so I'll also tell you a bit about this. So suppose this is the body and this is the body and it's rotating in an angular omega. It is rotating at an angular velocity omega and there's no angular acceleration. So what will happen to the torque? The torque will be 0. What will happen to the torque? The torque will be 0. Now we discussed impulse. Should I tell you about impulse? You remember what impulse is? In our previous chapter, we discussed impulse, in which impulse was change in momentum. Similarly, there can be an impulse due to torque. So impulse due to torque, okay? Impulse due to torque will be equal to, from time t1 to time t2, torque into dt is equal to change in angular momentum. This will lead us to the principle of conservation of angular momentum. So suppose there is no external torque, so the body will keep on rotating at an angle omega, that is the same angular velocity. There will be no change in angular velocity, and thus the angular momentum will remain constant. And what will be its value? Its value will be I omega. Which I have written here. So when there is no external torque, the angular momentum will remain conserved. Now the next thing that I am going to teach you is, you will get very easy questions based on equilibrium. So in questions of equilibrium, we just have to apply two things. Number one is forces in all direction for a body in equilibrium is 0. We have done that a lot in Newton's laws of motion. And the number two thing is torque at any point on the body, torque across any point at the body, an axis passing through any point of the body will be equal to 0. So the torque net of the system will be equal to 0. So when the questions are of equilibrium, so in case of equilibrium questions, number one thing that we'll do is summation of forces net equals to 0, and number two thing that we'll do is summation of torque net at all the points on the system will be equal to 0. right? So these are most of the questions will come from this part. Very simple questions. R cross P is I omega, torque is equal to R cross F is equal to I alpha, kinetic energy rotation is half I omega square, torque is torque dt, and this is the torque dt is equal to the impulse due to torque, and when external torque is absent, the change in angular momentum will be 0, and when the angular momentum is 0, when the change is 0, angular momentum remains constant and it will be equal to I omega. Very simple. And then there will be equilibrium questions when the force net will be equal to 0 and the torque net will be equal to 0. You will get it in the figure. It will be said in the question that there is an equilibrium. You can figure out just reading the language. All they can do is twist the language, make the question lengthy, but eventually what will happen in such questions are just these two things. Okay. The next thing that we are going to study, is the rotational plus translational motion. The next thing that we are going to study is the rotational plus translation motion. So suppose I have this irregular body, some body, right? And it is rotating about this point Q. It is rotating about this point Q at an angular velocity omega. It is rotating about point Q at an angular velocity omega. Now here is a point P. Now this object is not just moving in a circular motion, but it is also doing a translational motion, and the velocity of the whole body in the forward direction is equal to VQ. So we have one VQ here and we have one VQ here. Now what is asked is so suppose this is the x direction and this is the y direction. What is asked is what is the velocity of P in the x direction? What is the velocity of P in the x direction? So suppose this distance between Q and P is r and the body is rotating with omega. So we have to remember this result. And apply it directly, that Vp is equal to VQ square plus R omega square plus VQ square plus R omega square plus 2 VQ R omega cos of theta. Now what is theta? Theta is the angle. So suppose this is R omega. Now the angle between R omega and VQ is theta. The angle between R omega and VQ is theta. So VP in the x direction will be VQ square, that is the motion of the body of Q in the same direction. But okay, so here I did a mistake. What I wanted to say is the point VQ is moving translationally in a velocity VQ, but the point P in the x direction won't move at velocity VQ. It will move at a different velocity, and the formula for that velocity is VQ square plus R omega square plus 2 VQ R omega cos theta. As simple as that. Now direct formula questions will come on this thing, that what is the suppose there is a rotation around the center of mass. The rotation is around the center of mass. Now the direct question that will come is what is the total kinetic energy of the system? What is the total kinetic energy? So it will be kinetic energy rotational plus kinetic energy translational. Okay, translational, rotational plus translational. Now kinetic energy rotational, as we know, is half I center of mass into omega square. The body is rotating around the center of mass. And kinetic energy translation is, as we know from the chapter of collisions, half m into VCM square, right? So this is the kinetic energy. Next thing that we want to know is what will be the momentum, what will be the angular momentum. So angular momentum, total angular momentum. Okay, so we remember it is I omega, I center of mass into omega plus whatever the RCM is, whatever from whichever point we choose the origin, from that the distance of center of mass is equal to R vector CM. It is RCM cross momentum of the body in the translational or linear motion, which is m into vcm. Okay, so this will be the L, this will be the rotational plus translational angular momentum. So this was our topic, rotational dynamics. It is considered one of the most difficult topics, but it is just simple application of formulas since it is an objective exams, and you don't need to fear this chapter. I hope you enjoyed this chapter. It was a very good chapter, and keep subscribe to my channel, and I'll keep uploading more videos. Thank you.